Strong ground motions are known to also contain rotational motions. These rotational motions are also recorded by a classical seismometer. So in principle, every strong motion record is contaminated by rotational motions. This is what we try to fix with this work. Seismometers are inertial sensors. They are sensitive to any acceleration that acts on their proof mass. So in principle, when the ground rotates in a seismic wave field, the projection of the Earth's gravitational acceleration acts onto the proof mass and disturbs the acceleration measurement. With newly available rotation rate sensors, we can measure these ground rotation directly and correct for this disturbance. We performed several experiments to test numerical methods for this dynamic tilt correction. One laboratory experiment, one experiment with a synthetic dataset, and one experiment with a dataset collected during the Mount Kilauea eruption in 2018. What you see here is the setup of the lab experiment. This is a tilt table with two instruments on top, a classical Trillium Compact 120 seismometer and the rotation rate sensor BlueSeis 3A. In this paper we demonstrate that dynamic tilt correction with direct measurements of rotation is possible. Especially for strong motion applications and for observations of very long periods, we recommend to include rotation rate measurements to make it possible to correct for dynamic tilt. So what we actually do in this experiment is we generate a reproducible tilt signal. So this is a classical Trillium Compact seismometer, and this is the rotational motion sensor BlueSeis 3A. And this is a step table, which simply goes up and down, and so introduces a tilt movement of this platform. This plot shows the reaction of the seismometer to the tilt steps. So the red line on top represents the BlueSeis 3A, so the rotation angle measurement, and the black line at the bottom is the seismometer measurement. You clearly see a linear increase of the seismometer mass velocity when the tilt angle is constant, so a constant acceleration acts onto the proof mass. After tilt correction, we see an almost flat line with some residuals left over. If we zoom in, we see that these residuals simply come from the lateral movement of the seismometer mass induced by the rotation. So why does this matter? Where are the applications for this? In principle, everywhere where strong ground motions and long period observations are involved. So this is on volcanoes, at the ocean bottom, and close to strong seismic sources. So the essence of this paper is we need to directly record seismic rotational ground motions to perform these tilt correction. Now, with the development of seismic rotational motion sensors, this is possible.